Hello, my name is Tianlan. I'm a master's student from E-Aviation Group at the Technical University of Munich. Today, I'm honored to present to you our recent work on aerial tensile perching and disentangling mechanism for long-term environmental monitoring. Forests cover approximately 30% of the Earth's surface and are crucial regions for the human society due to their importance for biodiversity, climate regulation, and ecological balance. The most mysterious part of the forest is the canopy. However, exploration of the forest canopy has been limited due to its physical location, 20 to 60 meters above the ground, and is often blocked by leaves and branches. So, how to access and collect data from such place becomes a significant challenge to the scientists. Traditional methods to access the tree canopy still rely on human intervention. They are expensive and pose safety risks to the biologists. Today, the aerial robots offer easier access to the canopy. Nevertheless, the flight time is strongly limited by the current drone battery technology. To solve this, researchers were inspired by nature and came up with the concept of perching technology. Specifically, the tethered perching concept shows excellent potential to reduce energy consumption for long-term data collection tasks. It's simple and stable, adaptive to multiple shapes, and also has low noise and disruption. However, the upside-down position after perching increases the difficulty of recovery and power consumption. Another innovative way to monitor the environment is to use suspended pods. This solution has many benefits. However, it has to be deployed by humans. So, the contribution of this work are, firstly, this work introduced a multimodal aerial robot system and framework for environmental data collection to get benefits from both tethered perching and tethered pod. Secondly, we implemented a ring mechanism to ensure that the aerial robot system can avoid taking off from an upside-down position. Finally, experiments were performed to assess the effectiveness of different perching and disentangling strategies, aiming to make the environmental sensing sustainable and efficient. The robot system consists of 5 main components: propeller guards, multi-rotor, ring mechanism, tether, and suspended pod. First, let's take a further look into the aerial platform and the ring mechanism. The aerial platform was customized as a transportation vehicle. A 3D printed ring structure is mounted on top of the aerial platform and can freely rotate around it. The tether is made of high-strength polyester fabric for high friction and abrasion resistance. The last part is the suspended pod. The pod has 2 ducted propellers to create propulsion for pitch and yaw movements and a winding system for up and down motion. This specific winding system is to ensure uniform tether alignment on the spool. As shown in the figure, this work also proposed multiple perching and disentangling strategies. Through the innovative approach of this work, we used a payload to assist the perching and disentangling process, thereby saving energy. The results demonstrate that the combination of these components is more impactful than their individual contributions. Flight tests were conducted to evaluate the energy efficiency of different perching and disentangling strategies. The corresponding energy consumption is illustrated on next slides. As mentioned earlier, there are 2 perching strategies. The first loop has been done by the drone, and the second loop can be conducted using the drone or the pod's propellers. Compared to perching only with the drone, using the pod's propellers reduced the energy consumption to only 22%. Similar to the perching process, the first loop of the disentangling has been done by the drone, The second loop can be done using the drone, pulse propellers, or the winding system. Compared to disentangling only with the drone, using the pulse propellers reduced the energy consumption to only 22%. But surprisingly, using the winding system for disentangling corresponds to only 1.5% of the energy consumption for disentangling only with the drone. To conclude, this work focused on designing a system that could reach above or inside the canopy and collect data. The system is expected to be able to reduce the workload of ecologists and increase their safety. Secondly, the system achieved significant energy savings by combining a modified tethered perching mechanism and a specialized pod. Finally, different perching and disentangling strategies were tested and evaluated. In future work, the following topics could be further explored: reducing the size of system components, adding additional sensing capabilities into the robot system, also improving the control capability and autonomy of the system. Thank you very much for your attention.